Before we get into the topic of estimated control system of Boeing 737 MAX and what we think went wrong, let's just get to know how an airplane works in just 30 seconds. First, let's get familiar with angle of attack or AOA. AOA is the angle between the wind chord and the airflow. To generate lift, AOA is usually around 2 degrees in cruising flight. But to create lift during takeoff, it is often more than 10 degrees because air speeds are low.
But again, if the AOA is too great, the airplane loses control or stall. That doesn't sound very good at all.
For you who don't know what does aircraft stall looks like, this will show you. Stall is an aerodynamic condition whereby air can no longer smoothly flow over an airfoil, resulting in a rapid loss of lift. So, to address this issue, Boeing came up with MCAS. MCAS is a system that automatically forces the nose down from high AOAs by controlling the horizontal stabilizer.
This is the estimated control system done to demonstrate how the system works. After the MCAS system receives a signal from the sensors, it generates an instruction signal to the stabilizers to make the necessary changes. The stabilizers receive the signal and rotates accordingly and forces the nose down. This achieves the MCAS's objective to prevent the stall condition, decreasing AOA. The output, however, can be overridden by pilots by manually controlling the stabilizer control and the runway stabilizer in the aircraft. Notice the summing junctions here. This means that the output AOA is a combination of actions of stabilizer control, runaway stabilizer, and horizontal stabilizer. This creates an AOA output which will then be measured by the AOA sensors in the aircraft. The AOA sensors then generate the data which will be compared to a desired AOA set by the MCAS. Notice the summing junction here. This means the signal being sent to the MCAS is the difference between the desired AOA and the previous output AOA. The difference will be noticed by MCAS so it can generate a corrective instruction to minimize the difference.
So, let's do a little recap on how the MCAS works. The high AOA is detected by the AOA sensors. This data is compared to a desired AOA and a signal is sent to MCAS to rectify this difference. MCAS then sends instruction to the stabilizer, forcing the nose down. This action can be interfered by pilots using the manual controls. This combination of actions creates a new safer AOA output, which will then be detected by AOA sensors again, and the whole process repeats.
The MCAS compares the difference of the output AOA and the desired AOA, sends the instruction signal to the stabilizers. The stabilizers rotate and forces the nose down. This process is repeated until a safe AOA is achieved.
Seems like a pretty good system, but this system is often blamed for the disasters of the aircraft. So, what could possibly go wrong here? Here's what we think. First, the AOA sensors might be feeding the MCAS wrong data. This might cause the MCAS control to continue pitching the nose down into a very dangerous dive. It is also possible that the MCAS do not send the correct instructions like expected. The instructions given by MCAS could be too aggressive that it forces the nose down steeply. It is also possible that the pilots did not fully understand the MCAS and try to override it using the manual controls, but it might be too late to do so. As long as the problematic system is not shut down, any effort done by the pilot will be pointless as the MCS will continue to receive wrong data and give wrong instructions. In conclusion, we believe that a more detailed review should be done on the control systems to ensure it is fully functional and safe. This has to be done to prevent tragic disasters that should never happen in the first place.